Okay, let's move on to talk about the challenge problem of the chapter 12. It's about circle. So before we move on to the actual problems for the circle, I want to give some the initial important results. So if we have a chord inside the circle of the O, so let's see this is the A, B, and then if we have a tangent line of the L is tangent line, so if we see this is the theta, then I want to prove the any inscribed angle, okay, that spanned by the arc AC, bar arc AB is also theta. For example, we can connect it to the AO and extend it to the C. So the one I want to see is that this is the theta, then the inscribed angle spanned by the arc AB. Let's use another color. So you can see it's the arc AB. Okay, so this angle is also theta. So this is very useful for to use the tangent. Okay, so let's prove it. So we know the tangent line, right? So from the center O to the touch point is 90 degrees. So if this is the theta, this will be 90 minus theta, right? And we're extending this the radius to the diameter. So the diameter with the arc is the 180 degrees. So that's why the inscribed angle is half of that is 90 degrees. Okay, so now we can see if we know the 90 degree minus theta, this is 90. So that's why this plus this is 90 degrees, so this is the theta. Okay, so that means the angle of the arc AB is 2 theta. Okay, so this is very important result, and we always need to use. And the other one is if we have a chord of the AB, then we have the arc AB. Let's see, this arc is 2 theta. Okay, that means the centric angle means the AB with the center of the O, this is the 2 theta. Okay, then the any inscribed angle, okay, the any inscribed angle of the ABC, okay, so this angle will be theta. Okay, so if arc AB is 2 theta, then the inscribed angle is will be half of that. This is very obvious if you can see of the diameter. That's the special case. This is the diameter of the AB, right? So this is the half of the circle, so that is 180 degrees. So when you span any angle here of the C inscribed angle, so this is always the 90 degrees. Okay, so with all this knowledge set aside, okay, very important knowledge. Okay, with all these informations, now let's see what's going on here. Okay, so let's connect it with the A and the C, right? So you can see C is the touch point, right? So this angle of the BC arc, right? This angle 50 will be the BC arc of the inscribed angle. So BC arc is 100 degrees, and this is 50. And the same thing, right? It's tangent line, so it's the AB arc. The AB arc will be 80 degrees, so this will be the 40 degrees. So 40 plus 50 is 90 degrees. Then you can see this one is 90 degrees. If you know this one is 90 degrees, right, then what you get is the AC is diameter. Once you know the AC is diameter, you know the ACO collinear, where O is center of the circle. So here is the O, right? Okay, and you know the OC is 90 degrees, the OA is 90 degrees, because the L is the tangent line and M is the tangent line. So now you can see it's 90 plus 90 is 180. From this 180, you can see L parallel to M. Okay. Yeah, I leave all the process. You can write the process based on the discussion. Okay. So this one is the, so we have a parallelogram of the, we have the ABCD is the parallelogram. ABCD is a parallelogram. Okay, so if ABCD is the parallelogram, then we can do the B6 tending to the point E. What we want to show that is the ED is equal to CD. Okay, so parallelogram, we have alpha, then this is the alpha, right? So if you know the BAD is alpha, right? The BAD is spanned by the arc of the BD, right? So this arc is 2 alpha, right? So if this arc is 2 alpha and this arc also expand the angle of the BED, right? So BED is half of that, so it's alpha. So now you know it's alpha and alpha, right? And what does it mean? That means the EDC is a isosceles triangle. Then you can see ED equals CD. Okay. Next. So yeah, I mean, you from that problem we can see the angle tracing along the circle is very important. Okay. Next is ABC is a right triangle. Okay, so we have ABC. Let's see, this is the right triangle. Then we have the radius, right? The in radius is the in circle. That's the intersection of the three angle bisector. Okay, so now we know this is the in center. Then we can see this is the R, this is the R, right? So we have 90 degree, 90 degree, 90 degrees, and we have 90 degree. This is the rectangle, and with the two adjacent sides equal. That's why this is the square, right? So let's see. This is the D, E. A is D, E, F. Okay, so now we know the radius is 5, right? So it's 5, 5, and 5. If the perimeter of ABC exceeds twice of its hypotenuse by n, right? Let's see what is the perimeter. The perimeter is A and B and C, right? So it's A plus B plus C. Okay, then you can see because this is the R, right? This is the 5, this is the 5, right? So you can see the A plus B minus C is equal to the 2R, okay? Then let's see, this is the perimeter, and the question is asking you to let the perimeter minus the 2 times C is equal to the A plus B plus C minus 2C is A plus B minus C is 2R, right? Then we know the R is 5, so that the answer is 10. Next is so A, B, C, D be a point on the circle in that order, okay? So let's do this. Of circle, then we have the A, B, C, and D. Okay, so we have inscribed quadrilaterals, okay, cyclic quadrilaterals, and let PQ be the point of the, okay, so now let's see, this is the P, it PA bisect the angle DAB, okay, and CQ CQ bisect the angle BCD. Okay, so this one bisect the angle A, this one bisect the angle C, right? So it asks you to prove that PQ is a diameter. Okay, so if PQ is a diameter, okay, it's equivalently to prove that PCDQ is half circle, right? Is 180 degrees, right? So now let's see. So this is the half of the A, right? So we know BP is the A because this angle is A divided by 2, right? So this angle, the BP arc is A, right? Then we know the PD arc is also A, right? Let's assume the PC arc is X. Then the CD arc is angle A minus X, right? Because the PAD spanned by the PCD arc is A over 2, right? So that's why. And now we have the other side. We can do the same thing, right? We know the QD arc is equal to the C, right? And we know the ABR, for example, this is the Y, then the AB arc is the angle C minus the Y, okay? Now let's see, what we want to prove is the PCDQ, right? So let's add together. So PCDQ arc is X plus angle A minus X, then plus the angle C is angle A plus angle C, right? So this angle A plus angle C, but ABCD is a cyclic quadrilateral, right? Means the angle C plus angle A plus angle C is 180 degrees. So that's why we can see the PQ is diameter. Next. So we can let the in circle of the tangent A of the ABC be tangent to the sides, okay? DEF, okay? So let's draw a ABC. We have the ABC, then we have an in circle. That's the in center is the intersection of the three angle bisector, right? So the tangent to the sides of the BC and tangent to the sides of the AB and tangent to the sides of the CD, right, is DEF, okay? So you can draw a circle, okay? But if you are familiar with, you don't need the circle, and once you draw the land, the three height, okay, the three altitude, that's good enough. Yeah, let me draw the circle here, okay? Yeah. Okay, so now we want to let's this line because it's the angle bisector. Given the A is 32, so this is 16 degrees, this is 16 degrees. We try to find the EDF, okay? We try to find the EDF. Okay, now let's see, okay? So we can see the first, there are many cyclic quadrilaterals. For example, the CFID is a cyclic quadrilateral. Why? Because this is the touch point, right? I is the center, right? So you know this one is 90 degree, this one 90 degree. So the opposite angle adding to the 90 degree. So that's why the CFID is cyclic quadrilateral, right? So if they are cyclic quadrilateral, so this is the half of the C, then you know this is the half of the C because they all spanned by the arc of the FI, okay? Now the other thing is you can see there is another cyclic quadrilateral. Okay, so it's the EIDB is also cyclic quadrilateral because 90 degree and 90 degree on the opposite sides. So this is the B over 2. So this is also the B over 2, right? So now you know now you can see the angle EDF is equal to the C over 2 plus the B over 2, right? Because ABC are the triangle, so it's 180. So half of this is 90 minus the A over 2, right? The half of the A over 2 is 16. So 90 minus 16 is 74. Next. So this one is the AB is the diameter of the O. So let's draw a circle. So let's see, AB is a diameter. This is the center. This is the A and the B. Okay, then and the AX and AY are the chord. So AX and AY are the equal chord. Okay. So prove that AB is the perpendicular bisector. Okay, so we know they are the equal chord, right? So we want to prove this is the perpendicular bisector. For example, this is the D, right? So we know this is the alpha, this is alpha, right? So this arc is 2 alpha, AY, right? This arc is 2 alpha. Okay, and then we know the arc of the AXB, because AB is the diameter, right? It's 180. So this arc, the BX is 180 minus 2 alpha, and the BY is 180 minus the 2 alpha, right? Now you know this one is what? This one is 90 minus alpha. Since this one is 90 minus alpha, you know this is 90 degrees, right? Okay, since you know this is 90 degrees and XAY is an isosceles triangle, then you know this is also a bisector, right? So that's why it's the perpendicular bisector. Okay. Now find the XZ. Okay, so the problem of that is this is the XZ. Okay, so we have the X is a right angle, XZ and the Y. So we have the we have a in center of the I. Now we kind of have the touch point, right? Here is the touch point. Okay, then we know the touch point, for example, is PQR, and we know this is the length is the 6. This the length is 3. Okay, so we know the triangle XYZ is a right triangle with x equals 90 degrees, and we know the touch point of in circle at PQR, and the YR is 6 and the ZQ is 3. So we want to solve what is XZ, right? So you can see to solve the XZ, right, you need to solve the radius. Once you solve the radius, this is 6 and this is the 3, right? But because from one point to the tangent to the circle, okay, to one circle is also equal. So now you can see is we have a Pythagorean theorem, right? So the xz is equal to 3 plus r, then xy is equal to 6 plus r, and yz is equal to 9, right? Pythagorean theorem tells you 3 plus r square plus 6 plus r square is equal to the 9 square. Okay, then we can try to solve it. Is 2r square plus 6 and 12 is 18r, then plus the 9 and the 36 is 45 minus 81, so equals 0. Then you can solve is r squared plus the 9r, then this is minus the 36 minus 18 is equal to 0. Okay, so now you can try to use that delta is equal to 81 plus 72 is 153 is equal to 9 times the 1 and 17. 9 times 17 is the so now you can solve the r is half of the negative 9 plus minus 3 negative 17, because the radius must be positive number, right? So you can get r equals to 3 square root of 17 minus 9. Okay, once you get the r is 9, then you can solve the xz is equal to 3, then plus the 2 of 3 root 17 minus 9, then you can get is 2 3 root of 17 minus 3. Okay. Next is so we have two square next to each other, right? And we have a circle is the center, right? So you can draw the center of the square is also the center of the circle. Okay, so let's see, this is the A, this is the B, and we know this is 256, so that's why its side is 16 and this side is the 4, right? So we want to calculate what is the length of the AB. Okay, so this is very simple. We can land on here, then you can see it's the 4 and the radius is 2, it's the 16, right? So that's why this is 2 and this is 8, so this is 6. Now we can see 8 and 2, now this is the 10. Okay, so now you know the AB is equal to the 10 square plus the 6 square. Okay, next. Given a circle of the radius of the 2, okay, there are infinite many lines segment. Okay, so I have a circle of the radius of the 2. Okay, so there are infinite number of lines that are tangent to the circle. For example, it is tangent to the circle, okay, and at the midpoint, this is the midpoint, so this is the 1, this is the 1, right? This is the A, right? So you can see the question is said, find the area region consists of all such line segment. Okay, what's the area by all this line segment? Let's draw some line segment here. This is the point, right? And we know we can draw another one. That's this one, right? It's also 1 and 1, right? So you can imagine, okay, if I have another one here, right? So basically the area will be constructed by, if I have infinite number of such tangent, the area will be expanded by the circle that is the radius of the QA, so of the OA, right? So the OA is equal to this is the 2, this is the 1, right? Is 2 square plus 1 square is equal to root 5. So the whole region will be the pi times root 5 square is 5 pi. So the C1 and C2 be the two circles that intersect at A and B, okay? So we have two circles. Okay, we have it's called the C1 and the C2. They are intersect at point A and point B. Okay, so P be the point diametrically opposite to A against the C1. So that means P is here. Okay, so and the AP is diameter of P1 of C1. Q is the point diametrically opposite to the A on the C2. So AQ will be the diameter of the C2, right? We want to prove that P, B, and the Q is a line, is collinear, right? So let's do it. So let's connect the AB, and you can see because the PCA is the diameter, so this is 90 degrees, and the AC to Q is also diameter, so this is 90 degrees. That's why, since the angle, so that's why the angle PBQ is 180 degrees. Also, it proves that the PBQ are collinear. Next, so chord CE is a perpendicular bisector of radius of A. So let's see, okay? So we have the O and the A is the radius, and the chord CE is perpendicular bisector called CE. So it cutting this radius into half and half, right? And the AX is the diameter. So let's extend this. AX is the diameter, so this is also the R. And we want to find the angle of the OCX, okay? OCX. Okay, so let's add the line of this, okay? Now let's see what's going on. So this is the R, and this is the half of the R. This is the 90 degrees, right? Because we see it says that CE is a perpendicular bisector of OA, right? So that's 90 degrees. So if you have the hypotenuse of R and this half R, so this is the 30 degrees, right? And so this is the 60 degrees. Okay, and also you can see this is the isosceles triangle, okay? The XOC is the isosceles triangle. We have this 60 degrees. So this is alpha, this is alpha. So 2 alpha equals 60 degrees. So you can see alpha equals 30 degrees. Next. So this one is we have a tangent things. Then we know the AB is equal to 6. The BC is equal to 7. And the CD is 8 and AD is 9. Okay, let's parameterize it. So from B, because they both are tangent here, right? So we know it's X and X. Then we can parameterize the A touch point is 6 minus X, right? This one is 7 minus X. and this one is also ax is also 6 minus x, right? And dx plus 6 minus x will be 9, so this one is 3 plus x. Okay, now let's see, we after parameterize, we know the cy is equal to 7 minus x, and the dx is 3 plus x, then they add together is 10. Next, so we have this region, right? So this is the center of the O, right? Okay, so now it mentioned the center of the O with the 2 half semicircle with the radius, and the small one is contained in the large one. The room shown in the right above. The furthest distance between the 2 points with a clear line. The furthest point must be somewhere from here and tangent to the small one, right? Tangent to the small one, and to make it as long as possible. So that's why this is the touch point. You know the touch point is 90 degrees, right? So this is the large radius is y, small radius is x, right? So the region of the semicircle, two semicircle, the difference is pi times the big y square over 2 minus the pi times x square over 2, right? So this is the region we want to calculate. Okay, so the goal, what we want to know is what is the y square minus the x square. Now let's see. So the longest radius is 12, right? So here is the OT is cutting this chord of the big on the chord of the big circle. So this is 6. Now by the Pythagorean theorem, we know the y square minus x square is the 36. So this one is equal to the pi over 2 times the 36 is 18 pi. Next, so the incircle of the ABC is tangent to AB. Okay, let's draw it. The ABC, the incenter is the angle bisector. So this is the I. Is tangent to AB at Z. AB at Z. If the radius of ABC is equal to AZ. So let's see, this is the R and this is the R, right? Let's do this. So this is also the R because this is the incenter. And by the symmetry, right, because this is A over 2, this is the A over 2. So we have two angles are the same and a common side, so this is also the R. Then the angle BAC is the right triangle. Okay, so we can see we have the R, and the two of them are the R is what? The R, it must be a rhombus, right? It's a rhombus, right? Once it's a rhombus and once there is one angle of 90 degrees, they are parallelogram, right? So this must be 90, right? So that's why this is also 90 degrees. Okay. Next. So the side of the right triangle ABC, we know this is A, this is the B, this is the C. We know the ABC belong to integers. Okay, so prove that the in radius. Okay, so here is the in radius. For the right triangle, it's very special because here is 90 degree, 90 degree, 90 degrees. So R. So we know this is the square. Okay, so we know the 2r is equal to the a plus b minus c. Then the r is equal to the a plus b minus c over 2, right? So the goal we want to prove is a plus minus b. We know they are integers, so it must be is equal to even number. This is the goal, right? Okay, now let's starting from the a squared plus b squared equals c squared, okay? So now let's see, okay? So from here we know the a plus b squared minus c squared will equal the 2ab, right? Okay, and this can be factorized as a plus b, then plus c, and a plus b minus c equals 2ab, right? This side is an even number, right? And we know the a plus b plus c and the a plus b minus c, okay? What they could be is the even or odd, right? So on the right side is an even number. So all times odd must be odd, right? So there's no way to this. So there must be even number. So that's why this is an even number. Once you know this is the even number, so this is the integer. Next. So this one is let omega be the circumcircle of ABC. Let's draw. Let's draw. Always circle is hard to draw, right? And triangle is easy. So that's why we always draw the circle first. We draw the ABC. Okay, and we know the A1, B1, C1 are the midpoint of the arc BC. This is the A1, then this is the B1, and this is the C1. Okay, so we want to prove that the incenter, that is the incenter of the ABC. The incenter of the ABC is the angle bisector, right? And is the orthocenter of the A1, B1, C1. A1, B1, and C1. Okay, so what you can see is this is the arc. These two arcs span the angle A, right? So that's why this is the angle A, this is the angle A, the arc, because half of the 2A is A, right? Similarly, we know this is the angle B, this arc is angle B, this arc is angle C, this arc is angle C, right? And 2A plus 2B plus 2C is the whole cycle, okay? So now we can see the AA1 is the angle bisector, right? And the BB1 is the angle bisector, right? So this point I, okay, is the incenter of the triangle ABC. Okay, now let's prove this. Now let's prove this I, okay, let's prove this I is perpendicular, the A1I perpendicular to B1C1, okay? Now let's see. So we can see, okay, so the C1 C1B1B, okay, is the angle C, right? Is the arcs of the angle C, right? So this is the C over 2. Okay, the A1B1B is the arc A, so this is the A over 2. Okay, and the A1B1 is arc of AB is angle B, so this is the B over 2, right? So you can see this angle plus this angle is half of the A plus half of the B plus half of the C is 90 degrees, which means this is 90 degrees, okay? So this we all use the angle tracing along the arc, okay, to make it see it very simple. Similarly, we can also prove this is also 90 degrees, right? the 290 degrees means, I'm sorry, we can prove this is 90 degrees. The 290 degrees means the I is also the orthocenter of the A1, B1, C1. That's it. Next. So prove the quadrilateral of the ABCD. So this is the is cyclic, right? Now let's see. Now let's intentionally draw it outside. Okay, A, B, C, D. Okay, so it mentioned the ABCD. The ABCD is the angle A plus angle C is 180 degrees, right? So you can draw a circle of the let's draw a circle around the BCD, right? So there is an arc to the BCD, right? So this the BAD arc is 2C, 2 of the angle C, right? And of course, I mean there is the BCD arc is 2 of the angle A, right? You know the angle A plus angle C is what? Is 180 degrees, right? That means the BAD arc plus the BCD arc, okay, will be the 2 times 180 is 360 degrees, right? So that means the BAD arc and the BCD arc kind of getting into a circle. So that means the ABCD is concyclic. So next, we are given points ABCD in the plane. So we are given point ABCD, so we have the AD equals 13. Then we have the ABC, ABC, CD. Let me redraw it. A, B, B, C, C, D, A, D. Okay, so A, B, B, C, C, D. So we have 10, 10, 10, and 10. Okay, so what we can see is we have this one is 60 degrees, 60 degrees, and 60 degrees. Right, so what we want to try to solve what is the angle of ADB. So let's say angle ADB is theta. Then we know that this is the BCD is isosceles triangle. Let's say this is the X. Then the ACD is also isosceles triangle is X plus the theta. Okay, so how can we solve the theta, right? So let's see, we can see the, okay, so we can solve this angle, right? This angle will be the 180 minus the 2 x minus the 2 theta, right? This is from the triangle ACD. Okay, then we have a isosceles triangle BCD, right? So we know that from the BCD, we know the 2x plus 60, then plus the 180 minus 2x minus 2 theta, then this together is 180 degrees, right? Yeah, so now we can 2x plus 80, yes. So now we can see the two, we add them together, we can see the 240 minus the 2 theta is equals 0. Then theta let me see. So 180 minus this, so we have the yeah. Next. Let me see, something wrong. 180 minus 2x minus 2 theta, then it's x 60. Oh, okay. Okay, it's 2x plus the 180 minus this plus the 60. Mm-hmm. Okay, I make a stupid mistake. Then we have the theta, we have the 2 theta is equal to the 60, and theta is equal to 30 degrees, okay? Because this angle plus the 60 plus the 2x is equal to the 180. It's the same, okay? Sorry about it. Okay, so the final one is the PQ be a diameter of a circle and T be a point on the circle besides the PQ. Okay, so let's draw a circle, and this is the O. Then we have the PQ is the diameter of the circle, and the T is another point here. Then we have the tangent to the circles through the Q. So we have a tangent line through the Q, and we have the PT can intersect with this line at the R point, and the tangent through the T. So we have another point tangent through the T is M. Okay, so normally what we always do is we connected the center with the touch point. So here is the 90 degrees, here is the 90 degrees, and we can connect it the QT, right? So here is some angle angle chasing. Here is the alpha, right? Then you know from the M is touching point to the T and the touching point to the Q. So the MQ it will be equal to the MT. And this one is also alpha. And so this arc, the QT arc is 2 alpha. And this angle is alpha. And this angle is alpha. So we have many direct angle chasing from here. Then it says the PQ is a diameter, right? So that's why this angle is 90 degrees as well. Now we know that this angle is 90 degrees. Okay, since we know this angle is 90 degrees, right? So we know the triangle, the QTR, is a right triangle, right? So we know the QTR is right triangle. It's right triangle, and we also have the QT equals QM, right? I'm sorry, QM equals MT. Once we know the QM equals MT, right? So only the right triangle have because this is right triangle, this is the radius, right? Means the QM equals MT just means M is the center of the M is the center of the circumcircle of triangle QTR. Okay, so that's why you have the QM equals MT equals RM. Okay, so that's it for the challenge problem of this chapter. Thanks a lot. Bye.